Please hold while your passcode is being verified. Please wait for the tone, then say your name and press the pound key. At the tone, you will be the fifth caller in the conference. To mute or unmute your line during the call, please press *6 at any time.
Actually are about the same if you look at them in Insight Explorer. So a lot of these topics will kind of transfer over. I will mention Insight a couple times that we will be focusing primarily on the DVT Intellect software here. So first thing we want to look at is just general filter uses. Why would we use a filter? A couple examples here. One of the most common reasons why you'd want to use a filter on an image is to increase contrast. In this scenario, perhaps it's for counting, perhaps it's for finding edges. It can be for anything, but generally just to get better contrast so that your inspection is easier. In these images on the upper left corner, you can see we have a bunch of rolls of paper and pretty low contrast, pretty difficult to count. You can apply a filter to these and you can see that the centers of each of these rolls is a lot more apparent. So in this case, the image is a lot easier to inspect with a counting tool. Another common use for filters is color thresholding. The color tools in Intellect allow you to learn colors and indicate where those colors are and count the number of pixels and so on. But if you want to just threshold the image with that color, you need to use a filter. So in this top right image where you have Skittles, we can learn the color green and then use a color filter to threshold that to make them much easier to identify. Likewise, in the bottom right image, we have a picture of a fish fillet, another color image. In this case, we're not just using a color threshold, but we're actually using the color planes to isolate a specific region of the image, in this case the spine of the fish. On the bottom left, we see an image of a barcode. This is a very good use of filters, doing FOV balancing. You can see on the image on the left that we have a bad gradient of light. It's very bright on the left and very dark on the right. This makes it a little bit difficult for tools which are looking for edges to find those edges because they can't use the same threshold across the whole image. If we apply an FOV balancing filter, we can actually even out that light intensity. And so an FOV balance filter is used anytime you want to learn what the lighting is actually like on your part and then apply a correction. This is applied specifically with a filter instead of being applied to the whole image, which is kind of a new concept in Intellect versus the old framework software. So that's just kind of a general look at some of the things you might use filters for. One of the things we want to cover is just what is an image filter. So an image filter is just like any other filter in the world. It takes something in and it spits something different out. A lot of times that means stripping things away, but for the most part it just means changing the composition of something. So an image filter is the same. You take an input image, which is your original image, and you output something different. The goal being to enhance the feature of interest so that it's easier to inspect. This can include actually enhancing that specific feature or suppressing noise around that feature. Both have the same effect, hopefully, of making the image easier to inspect. So looking back on one of these images that we've already seen, the original image, when we try to count these rolls of paper, we can use a blob tool on an unfiltered image and we can get decent results, and we could probably tweak this a lot more and get better results than what I have here. But you can see some of the parts are a little bit noisy because the ridges between the sheets of paper as they roll around are dark, just like the center. So it kind of throws our blob tool off. If we use a filtered image instead, we can get rid of a lot of that noise. And our blob tool is much easier to use without having to tweak it a lot and without having to worry about maybe subsequent images causing problems. So that's the basic use of a filter. Just make the image easier to inspect. Some of the common applications that we see for filters, color counting and sorting is one of the big ones because, as I mentioned, the color tools need to use a filter if you want to threshold based on that color. So any kind of counting of something colorful, sorting that, doing measurements specifically on that, and getting rid of background features, defect detection on specific regions of color, these are all applications where a color threshold filter will probably come in handy. FOV balancing, or field of view balancing, another common one like we saw on the barcode application. This is instances when the illumination on your part is not even and you can't really correct it. This could be perhaps because the part itself is a little bit uneven, and it's always going to be that way. It's hard to get a light to correctly illuminate that. You may need to move to a custom light, which may be unreasonable. So FOV balancing can be a good solution. OCR is a place where filtering is particularly handy because a lot of OCR codes are in the midst of other text, other barcodes, other features in the image, especially if you're looking at labeling applications. And this other background text and other features basically are noise. So you can use filters, and specifically a blob threshold filter, to get rid of some of that background noise. We'll see an example of how that works. Defect detection is another place. In defect detection specifically, you're looking a lot of times at edges, because edges are where you see defects. Or defects show up in the image, and they basically, the defect itself is an edge. So you can use filters to enhance edges and to sometimes minimize edges so that you don't get extra defects and so on. So these are 4 good applications. See these a lot when using filters. We'll look at some of these in image examples as we go on. So here's an example of a color counting application. This is an auto fuse box. You can see we've got a bunch of different fuses, 10 amp, 15 amp, 30, 20, and they're all different colors. So if we want to verify the location of a fuse and make sure that it's got the right fuse in the right place, there's kind of 2 different approaches we could take. One is we could try to read the text. And for something like this, that may be a little difficult. The text isn't particularly clear here. It's a little bit easier in this scenario to go by color. So we can use a pixel counting tool on a color camera to learn, in this case, the red 10 amp fuse, and then use a color threshold to filter out everything but that red color. So that's what we see in the bottom left image. We see an image where we've applied a filter over a specific section of the image, and that's just the black box that we see there. And everything but that red color has been thresholded out. Now you probably noticed that it's not just a single red color, but it's actually kind of a complex histogram of red. So that's one of the great uses of a pixel counting tool in conjunction with a filter, is that you can learn a complex histogram, not just a single color, but a whole range of colors, and then threshold based on that. So it's a very powerful thresholding method. Once we get that filtered image, we can apply tools on top of that filtered image. In this scenario, we've used a blob tool just to verify that we've got, in this case, 6 filters. Now we could go on beyond that and get the locations of those blobs and make sure they're in the right places, and apply some criterion to the blob tool to make sure that there's the right size and so on. Good application for color tools. So FOV balancing. This is the image that we already saw up above, a little bit more detail here. The red box is a 1D code reading tool, so basically just trying to read this barcode. In the top image, we are not able to read that code because none of the thresholding methods will quite allow us to pick up the edges both on the left side of the image and the right side of the image where the contrast is much lower. If we are only focusing on one region, we could probably set a threshold that would work, but having to kind of dynamically create a threshold across that region is a little difficult. So you see in the bottom left image, we don't get a read. If you're not familiar with the barcode tool, you would see a green X on the left and right of that box if we were actually getting a read. So to correct for this, we use the FOV balancing filter, and what we have to do is basically learn the background illumination. To do this, you would typically use a white sheet of paper or some kind of blank surface that represents the surface of your part. Now, if you're looking at some kind of broad flat part, you can literally take a piece of paper and lay it down over the top of your part and turn on the illumination and take an image of that. That's what we have here in the upper right image. It's just a plain white piece of paper that represents the illumination in the image. We learn that, and that allows the camera to calibrate how the pixels should be raised in intensity or lowered in intensity so that we get a perfectly even illumination. That is applied to our original image, and what we get is an image on the bottom right, which appears to have a fairly even illumination. Now you can see kind of over towards the right of the image, it looks a little bit grainy, and that's because I actually used just a regular sheet of paper. So the surface is a little bit bumpy. If you use something a little cleaner, you get better results. But nonetheless, we get a good read in this image. You can see there's the green X's on the left and right indicating that the tool is able to find the code and decode it properly. So here's an example of an OCR application where you're filtering out noise that isn't at first glance noise. You can see in the top right image that we're trying to read a code that sits below some other text in the barcode, and it sits to the right of yet some more text. So all this stuff is supposed to be there. But the problem is you have to apply the OCR tool only around the text that you're interested in. And if other features interfere with that tool, then you can get a bad read. Not only that, but in this example, we have to first position the OCR tool. Now, one common problem in OCR examples is that you don't have anything to position off of. In this case, you can see we've got a barcode, we've got the barcode text, we've got basically a lot code, the date, and all of these are changing from one image to the next because the parts are changing. So there's no consistent feature in the image off of which we can position. So what we have to do is use the fiducial tool, which was reintroduced into Intellect 1.4. This allows us to find a specific region of the image, in this case, to zoom in on the edges of the text and use that as a position reference. Well, the problem is that fiducial tool sometimes catches the edges of the text above it, and that's what you see in the bottom left image. The fiducial tool kind of catches the bottom of that 0, 1, and that throws off the position reference. The position reference in this case is created by the green box around the text. And you can see that that green box extends all the way up to the 0, 1 at the top. And we don't want that. So an easy way to get rid of this, and I use this a lot in OCR applications, is to simply use a filter that thresholds out anything touching the edges. And this is done with a blob threshold filter. What you can do is set it in this scenario to only pass dark text, which would also allow the dark text up on the border, but then you check off the box for the blob tool that says enable edge blobs. And you turn that off, which means these edge blobs at the top go away, and all you're left with is what you see on the right, which is just the text that you're interested in. Now your fiducial tool finds the correct stuff, and your OCR tool can be correctly positioned. It's a great way of getting rid of any other features around the text that may kind of interfere with positioning or the OCR read. Here's another application, and this is where we actually cross over a little bit into Inside Explorer. And this one's interesting because it's only using an edge filter and an image differencing filter. Now, an edge filter is something that you get in both the Intellect environment and the Inside Explorer environment. Image differencing is only a filter in Inside Explorer, but it is actually part of the defect detection tool in Intellect. So this is kind of an interesting application of filters in that in Inside Explorer you don't have a defect detection tool, but you can create it using two filters. So the process here, and I guess first let's talk about the part. The part in the upper right corner has 4 leaves to it. And you can see on the upper right corner, inside the red circle, that piece is a little bit short. And that's what we're looking for. We're looking for some of these edge defects where we might have a short shot on that molded part. If we take an edge image of it, which you see in the bottom left, we get only those boundary edges. And because we're looking for basically edge defects, what we'd ideally want to do is compare rather than entire 2 images. We'd like to compare just the edges of those 2 images. By taking the edge image of the original part as it should look and the edge image of each subsequent part and then comparing the 2, we can get a difference. and the differences represent any defects. So in Insight Explorer, in this case, we take an edge filter and we take a compare image filter, and what we get is the image in the bottom right, which highlights only the place where we have a difference, which is the end of that leaf or tooth in that part. This is a good creative way of kind of creating your own custom tool. And these exact same principles can be applied in Intellect to create your own tool. So this is a great example of how the two different software environments have very similar tools that can be applied in a little bit different ways to kind of achieve the same inspection results. So from here on, we'll look at a couple screenshots of images and just the kind of filter that they use, not necessarily a real application, but just the effects of using various filters. After going through this, we'll take a look in Intellect real quick just to see how we set up a filter, how we apply tools on top of it, and just kind of a run-through of all the filters that are available. In this first image, we've got a roll of paper towels, and paper towels always have patterns on them. In this case, they're colored. And in this specific application, we want to do some color monitoring to basically monitor the color quality of the print. It's a little bit difficult because it's a complex pattern, and the areas of color, the green or the blue dots here, are very small, which makes them kind of hard to inspect, hard to get a tool specifically on those. Well, what we can do is instead apply a color thresholding filter to this. Now, we used a pixel counting tool first to learn the blue color, and then a color thresholding tool to get rid of everything but that blue color, which gives us the color we want to inspect on top of a black image, which now makes it very easy to throw a color monitoring tool on here and monitor the color quality of those dots without the interference of kind of the noisy paper background. Another good color example, a ribbon cable, varying colored wires throughout, and we want to find the placement of all the wires by specific color so that we know that all the wires are in the right place. Now, we could throw an edge tool across here and count all the edges, but being that it's a color image, two adjacent colors may have very similar contrast as you move across the wire bundle. So for instance, the pink next to the orange won't have a particularly high contrast, but it may look very similar to the orange next to the blue when we're just using an edge tool. So this makes it a little bit difficult to identify where the wires are. One way to approach this is to instead go color by color, and in this case we can learn specific colors, isolate them with filters, and then use measurement tools or whatever we need to use to find the positions of these tools within the image or relative to the other wires. This is an easy way of verifying where everything is. Another field of view balancing example. This one's kind of clever. We've got two spotlights on a piece of text, and the reason this image may be difficult to read is not just because we have a little bit brighter light on the left than on the right, but because we have to apply a threshold across this whole region if we're using a single OCR tool. An option may be to use multiple OCR tools, but that's a little kludgy. We'd rather just use one OCR tool across this and apply one threshold. Because we have very good contrast in the middle of these bright spots and not so great between the two, we'd like to get rid of that. By learning that background illumination, we're able to get an image like this. A little bit psychedelic, but it provides much better contrast across the middle of the image. And this is going to be a much easier code to read. Kind of a made-up example here. This is something that we've used in the past to demonstrate PatMax and Object Locate and their abilities to find shapes under various conditions. In this case, the challenge is that we have opposite gradients. So in one case, we've got a black object on a white background. In the other case, a white object on a black background. And those actually create positive and negative gradients within the tools, which can mean that potentially they won't read unless you set them up right. It's much easier in this scenario to just apply an edge filter. in which case now everything looks the same. You don't have a black on white or white on black object. All objects are in fact the same. Another simulated example here, this kind of noise, bunch of quarters here, and you've got a bunch of speckles on it. This kind of noise is typically called salt and pepper noise. You don't see this as commonly anymore. Initially, this kind of noise came from bad video signals, bad pixels on a CCD. Bad pixels were most common on CMOS sensors, which could lose pixels but had calibration routines to get rid of those false pixels or to compensate for them. Sometimes I still see noise similar to this on applications specifically that involve sand. I've seen OCR applications on sandpaper itself, and that sandy quality creates a very grainy image that makes it difficult to threshold and define edges. For this kind of noise, we have very small spot noise. An excellent filter to use is a median filter. And you can see that in this image, it's gotten rid of all of those spots, but it's left everything else at almost a similar quality as the original image. So the features in the quarter haven't been destroyed. There's another filter you can use that's similar to this, which is simply a low-pass filter, which also tends to smooth out this kind of noise, but it has the effect of smoothing all the features you're interested in. That's where the median is strong. It doesn't have as strong a smoothing effect, but more of a removal effect of that high-frequency spot noise. So this is a great filter for that kind of noise in the background. Now, this image, we can see that we're doing a measurement or an edge finding inspection here. This is just a small part on a false noisy background, a piece of newspaper in this scenario. This kind of demonstrates two things. One, there's a lot of noise, and yet the edge tools can still get through that noise and find the correct edges, which is great. It means that the edge tools are doing their job. But what we see in this next image is that when I apply a filter, we can get rid of a lot of that noise, but still get basically the same result. We still find those edges. So the question here is, why would we use a filter when it seems like our tools can still find the edges that we want to find? Well, to get an idea of what the filter might be doing for us, we can look at the gradient graphs of these two tools. So on the left graph, we see the pixel gradient graph of the edge tool applied to the noisy original image. And what you see is we've got two strong edges, the leading edge and the trailing edge. Those would be the two large spikes on the bottom and on the top. But we have a lot of other edges also, and these present noise that potentially can be recognized as the edges that we're looking for, and they would be false edges. You can see on that left graph over to the bottom right, we actually have our threshold just crossing the peak of a negative gradient. That's actually the wrong edge. And this is probably just a piece of noise in the background. Now, we got pretty much the same result in the filtered image, but you can see in the graph on the right that what we've done is we've kept those strong peaks, but we've gotten rid of lots of other noise, so that we are much less likely to pick up false edges as the inspection goes from one image to the next. So this is a good demonstration of how a filter can enable a little bit more assurance that you're going to get correct results throughout your inspections. Now, one thing I want to stress here is that you have to be careful when using filters on high precision measurement applications, because the filter inherently changes the input image, and that is often not desirable. If you change the input image, you can't be 100% sure that the results you're getting represent the actual part, so you have to compensate for that a little bit. But if you're just looking for a position reference in your image, I think that's an excellent scenario where you could use a filter like this without having to worry about losing your measurement precision. So here's a code reading image, and if you don't see the part in the image, look a little closer. Maybe change the angle at which you're looking at your monitor a little bit, but there should be a very dim 2D data matrix code in the center. And it's on a almost a light gray or a cream colored background. This image has very low contrast. The difference in intensity of the code pixels versus the background pixels are only about 1 or 2%. So we're looking at maybe 5 to 10 pixel intensities difference. Now this is also kind of a made-up example, but it demonstrates very well what the histogram equalization filter can do, which is spread out the pixels in an image to create a much higher contrast. So this is the same image, but with the pixels pushed out. So basically, it finds the middle of the image histogram, and then it pushes all the pixels above that to higher values, and all the pixels below that to lower values, so that the histogram gets equalized. It gets spread out. So what we get is a nice dark code on top of a very light background. Good example of how to fix images with very low contrast. The same filter could have been applied to that original image that we looked at with the rolls of paper to enhance the centers versus the paper and the rolls. Here's an image from a line scan camera of very small dots on a windshield. So kind of the sun visor at the top of the windshield where the rear view mirror is. They have these dots that block out the sun. You can see there's hundreds of them. This is a very small section. And each of these dots takes up about 3 or 4 pixels square. With there being so many of them, it's very difficult to find if one's missing because it's hard to localize your inspection on each of these dots. So what we'd like to do is make a missing one stand out more so that one of our tools can more easily look for it. We could use a defect detection tool, but positioning on something like this is very difficult because there's not a real consistent shape here. It's hard to position on so many small shapes that can shift a little bit. Instead, we'd like to use a blob tool to find where that missing dot is. The problem is the missing dot is a dark blob, and it joins right in with all the other darkness in the image. So if we apply a clever filter, what we can get is kind of an image that's been inverted, but is also enhanced that one missing spot. Now you can see we've got lots of little dark blobs in this one, but there's only one large one, which is quite a bit bigger than all the others, which makes it very easy for a blob tool to come through here and find where that missing dot is without having to do too much fancy positioning or anything else. A great example of, in this case, using a custom convolution filter. We haven't really talked about the convolution filter, but perhaps I'll point that out in Intellect and go over in general what that is. So kind of a final note as we get to the end of these slides is, when do you want to filter? A lot of people try to tackle a filter, or I should say implement a filter right away when they see something bad in their image. So 2 things I want to point out regarding that. A lot of the tools are already using filters. As I said, a filter changes the image to make things easier to inspect. And one of the core filters is just an edge filter. Well, the measurement and positioning tools and the edge tools in all image processing applications are just big edge tools. That's all they are. They're just big edge filters. So those tools are already doing a lot of filtering and thresholding. So a lot of times you won't need to use a filter for those. Same with the FFD tool, flexible flaw detection. It's basically a big edge filter that applies some logic to those edges once it's found them. PatMax and Object Locate, same thing, edge filters with a lot of other logic behind them. In the Insight system, the new OCR read tool has a confusing background function that you can turn on, which basically gets rid of a lot of background noise. It's basically a noise filter. It's not so simple as some of the tools that we have available to us in the Intellect user interface, but nonetheless, it's already employing filtering. Blob tools, same thing. They're applying grayscale or binary morphology, which we haven't looked at yet, and then some thresholding. So the point here is a lot of the most common tools are already filtering. So you want to think about whether you can use some of the parameters at hand in the tools before moving directly to a filter. Because a lot of times you can get rid of background noise or enhance your features by just using those parameters. At that point, if you can't, you've already tried tool parameters, then perhaps at that point you can move on to actually using a filter. So this basically means we've already tried the parameters, we've already tried fixing light, fixing part presentation, camera and light angles, and so on and so forth. At that point, using a filter is a good option. And the reason you don't want to jump right into that is because a filter is another tool, which means that it can take up more processing time and it can take up memory. So you want to use it only when you need to. That takes us to the end of the slides. I want to jump over to Intellect so that we can take a look at just a quick demonstration of how to actually implement a filter. So here we have the Intellect 1.4 user interface. I'm in a 545 emulator, and we have yet again a familiar image. The filters are under the Preprocessing section of the toolbox, and there's only one tool. Draw it just like any other tool, and immediately you get the exact same general options as you get with all other tools, so there's nothing special here. The shape, you'll notice, is a rectangle, and there is no rotation. So filters have to be aligned with the image. So they're always rectangular and they're always horizontal and vertical edges. As far as the options go, this is where you have access to all the filters. Now these are grouped by type. So first I'll use a filter just on this image and then we'll go through the different types. In this case, I'm going to go to the enhancement filters. And I will use two different filters to kind of compare the difference between them. Histogram equalization is one that we saw applied to the 2D data matrix code. And you can see that when I apply a histogram equalization filter, it does a good job of separating the paper in these rolls from the dark spot in the middle. So when the histogram of these pixels gets equalized, it pushes a lot of those lighter pixels to even brighter intensity levels, while the dark centers, which are basically black or very close, stay at very low intensity levels. Now one problem that this does present is that even though it's done a good job, we can see that quite a bit of the pixel intensities in the paper itself are still pretty dark. And this might confuse the block tool a little bit when you're trying to threshold. You're going to have to set your threshold a little bit finely. So if we try a different filter, which is the optical density filter, what we get is actually a little bit more even results. The optical density filter is basically an inverse logarithmic filter. That means all the pixels are inverted and then they are remapped on a logarithmic scale. That sounds a little bit meaningless. It is mostly used in the color industry, where optical density is used to see how well a object reflects and transmits light. That's the original intention for this filter. However, it's very good in applications like this. You can see that the centers of each of these are very light, and the kind of paper circles here are actually very uniform in intensity. So we are getting something that's very easy to threshold at this point. Now, if I move on from there, and I'll open that back up, and I want to do some more filtering on this, I could apply another filter on top of this. Now, if I wanted to do that, I would go down to the aggregate filter and increase my count. What this does, notice on the left here, instead of one filter, I have three, which means I can kind of aggregate these filters. So I can go back and create my first one as the optical density filter. I can create my second one as, in this case, a threshold filter. I'm going to leave it as a blob filter, use light blobs, and I'm going to increase this threshold. And you see now, using a combination of two filters, I've got a great contrast in this image, which is going to make it easy to count these parts. So this is how most often they use a filter, I think, using an aggregate. So perhaps from the start you want to just go ahead and create an aggregate and give yourself a couple filters to use. and then you can combine them. If from here you wanted to go on and maybe apply a blob tool, you can just come down and grab your blob tool, draw it across the object. And the first thing you want to do is change the image reference. The image reference is set to the acquired image, but what you want to use is the filtered image. So I'm going to change that to Tool 1, which is our filter. Apply that. And now, let's see where we go. I'm going to do light blobs. And you can see that we've now grabbed some of these light blobs in the background. I won't keep going that because we're not talking about the blob tool today. But that's the general process you'll go through if you're using a filter. First, create your filter, your image looking like what you want. Start adding your other tools. Use the filtered image as your image reference. And make sure that the region of your tools being applied on top of the filter stay within the filter region. If you try to use that filter, or I should say, if you try to use that tool on that filtered image, but the tool moves off of the filter region, then you'll get an error. And then it'll indicate tool moved off image region or something like that. We'll take a quick look at the rest of the filters that we have available. I'll just kind of run through these to show you all the different options. First section is morphology, and actually I think I will get rid of the first two so that we can see the effects of some of these. You can always just change to no filter if you want to get rid of one of your filters. So the first one, we'll use a morphological filter. Now morphology basically takes pixels that are adjacent to each other and changes them based on their neighboring pixels. So it's kind of like an average filter where you look at a bunch of pixels next to each other and they all affect each other. In this case, it's not an average, however. It uses a min-max algorithm to either group pixels together and make them expand or make them contract. So here you can see, and I think I have something else applied by accident. There we go. A dilation. Now in this case, it's not a great example of a dilation. So let's isolate off region here. Dilate and erode are the two common morphology filters, and what they do is they cause dark pixels to either expand or contract. So they either grow larger, which is to dilate, or erode, which is smaller. So you can see up here that this dark edge has actually expanded downwards. This dark edge has expanded upwards a little bit. Not a very good use of it in this scenario. But in general, you can use this to erode away dark features. And if you use multiple dilations by expanding the area that you're looking at, then you can actually make a dark feature erode away. I'm sorry, you can make that dark feature grow larger, which means you're eroding away light features. The erode is the exact opposite. It's going to make the dark features actually go away. So it's kind of the same as dilating a light feature. Open and close, a combination of those two. You can experiment with that, see what kind of results you can get. Basically, the premise with open and close is that you do one dilation and then one erosion, and you have the effect of making something smaller and then making it bigger again. If anything disappeared in that process, then it won't ever come back. So it's a good way of getting rid of noise without affecting the edges of all the big features in your image. Then there's fill dark holes and fill light holes, which are kind of obvious. It looks for dark and light holes in the image and it fills them. So that's morphology. One important thing to notice here is that this is grayscale morphology, which means it doesn't operate on a binary image. It leaves all the grayscale values intact. If you use morphology on the blob tool, that will be in binary. So the result will be a black and white image. Noise reduction has two filters, a low pass and a median. We looked at the median filter, and that was the one that we used on the image with quarters. The low pass filter is basically a blurring or a smoothing filter. And you can see from this image here that it has in fact blurred those background pixels. If I turn the filter off, you can see that there's much more sharpness there in the image. Next filters are gradient filters, which are actually really neat, but seldom used because many of our tools already employ gradients. All the edge tools, as I mentioned, object locate, PatMax, all those tools are already using gradients. So a lot of times you don't need to use a gradient filter, but we did see one scenario where it can be useful in Insight Explorer. And occasionally, they can be very useful when using object locate to kind of help object locate find the edges more easily. You can apply a gradient filter to different directions. Full means edges in all directions. Vertical means they're applied only to vertical edges. Horizontal means only to horizontal edges. High pass is a high frequency filter. Tends to really enhance noise. A lot of times you don't want to do that. And then a curse filter is similar to a full filter, but it's a little bit more comprehensive. Thresholding filters do exactly what they say. We've got the blob thresholding filter, which we already saw. We change that to light and move this up to 60 or so. Oh, I don't have the other filter ahead of it, so that's not going to work. But this is just a basic blob filter. The other one that you'll see used a lot here is the color filter, which allows you to reference something that's been learned by the pixel counting tool and then isolate based on that color. So this is what we saw in the example with the Skittles. There's also an edge filter, which instead of doing what the edge filter in the gradient section did, it actually finds edges and then enhances them. So it doesn't just isolate the edges, but it adds pixels to the edges. So here you can see that the edges are still in place. The image is basically the same, but it's actually added dark pixels to those edges in an attempt to enhance them. Don't see this used very often, but it can be handy. And the last is a segmentation filter, and I don't think that'll be well on this image. But it basically attempts to go through and segment the image into blob regions. Here everything kind of looks the same, so it's not a good of it. Enhancement has most filtering options. A sharpen filter does what it says. It tries to sharpen the edges. I'll skip convolution for a moment. The image domain filter is something that you can use in a grayscale image to simply apply a gain. In a color image, you can use it to actually combine color planes, so the red, green, and blue color plane, to get your own effects by subtracting and adding weighted values of those color planes. Optical density filter, we already saw that one used. Same with the histogram equalization, we've seen this one used. And then there's a linear contrast stretch, which also falls in kind of in the same category as optical density and histogram equalization. It basically allows you to set a lower and upper limit. Anything below the lower limit is going to get pushed down to black, and anything above the upper limit is going to get pushed up to white. So you can create kind of that threshold so that you can really isolate a center part of the image to stay at its same intensity while everything else goes to black or white. So it's a good way to push the extreme pixels in either direction, all the way to 0 or all the way to 255. FOV balance. Now, we can't really use this one because we don't have a good FOV image, but the way it works is you open a calibration window and you have to learn a white image. In this case, I've already got one learned, and you can see when it's applied, it's a little bit funny looking. But if you've already got one learned, you just have to delete and relearn. In this case, we've got a lot of noise in the image, so it doesn't quite look right. But if we had a proper image to learn on, we could learn the background intensity, and then it would be applied only to this filter region. Subtract dark image is similar to FOV balance filter, but instead it tries to learn the dark image. So instead of putting a white piece of paper in front of the image, you would actually want to take an image with the illumination turned off. And this causes the camera to learn what the dark image should look like. And then everything from there on is brought up to that level so that you have a nice even floor, which means everything starts off at a 0 pixel value. Not often used. This originated from CMOS sensors, which could have kind of a noisy intensity floor. Don't really have to use this too much anymore. Last one is a flip image filter, which simply allows you to regions of the image vertically, horizontally, or both. Obvious what that one does. And that's the end of the filters that are available in Intellect. I encourage you to play with these. You know what? I did skip something. I said I was going to go back to it, and I didn't. The convolution filter. So the convolution filter is where you can employ your own custom filter. Now, this can grow up to a 5x5 size or as small as a 2x2 size. 1x1 wouldn't do much for you. And basically what it does is it multiplies pixels in the image by these values in this filter kernel. and it does this at each pixel location throughout the image. So in this case, it would multiply every pixel underneath this kernel by 1, add them all up, and then divide by, in this case, we would want to make it 25 because we have 25 pixels here. And this filter, in this case, would basically create a blurring filter. So we already saw that. We don't really need this unless we need a 5x5 or 4x4 blurring filter as opposed to a 3x3, which is the default. You can create lots of other filters if you know a little bit about filter theory, or if you just want to play around with them a little bit. For instance, if I create this filter, and I divide by 9, what I get, and I don't want to divide by quite that much, is a rough edge filter that's filtering edges only from left to right. So you can see we've got some edges going left to right, but we don't have any of the edges going up and down. Expand this a little bit. You can see the same thing up here. We're only getting those left to right images. So I can create a custom edge filter. This is what I actually used in the image that we saw of all those dots from the windshield on the line scan image. I created my own 5x5 filter, and I actually stacked 2 of them on top of each other to get the proper effects to isolate that missing dot. So if you want to play around with filters a little bit and kind of create your own, this is a good way of doing it. The values don't just have to be 1 and 0. They can be all kinds of values. Can't go into it too much right now, but you can get creative with them here. I encourage you to get creative with the other ones. That's really the only way to learn how to use filters, is to test them out, see what they do, see what you can do with them. That pretty much closes it out for image filters in Intellect. Anybody have questions or comments?
Thanks, Frank. This is Miguel.
Miguel.
I was wondering if I actually coincidentally received some images recently from a customer, and I was wondering if you would mind spending a few minutes on those images with me, and you can choose to do that either here with the folks as part of the recording or offline with me, however you thought it was best.
Let's go ahead and do that offline so we can kind of keep this on a specific subject, and then if we have to kind of divert on those other images, then we can.
Great, thank you.
Yep, no problem. Anybody else? No? Good deal. Well, it's Friday. Everybody have a good weekend. Thanks for showing up, and hope you learned something. Bye.
Thanks, Frank.
No problem. Bye, everybody.
Thanks a lot, Frank.
Bye, Dave. Thanks for coming.
Take care.
Yep, you too.
The moderator has disconnected. At this time, the conference will be terminated. Thank you, and